Hello, my name is Matthew Johnson. I work at Netflix, where I'm a senior DevOps engineer for the Insight engineering team. I've been around the information technology industry for quite a long time now, about 17 years. I've spent a bunch of time working with networking equipment, Linux servers, all sorts of different build-outs, storage and whatnot. Spent my time with Enterasys, NetApp, a few other systems like that. At a certain point in my career, after spending a bunch of time working at Blackboard, I got to the point where I was like, hey, you know what? It's pretty awesome to be able to build infrastructure with the power of your mind. AWS is a cool thing. I want to spend more time doing that. And Netflix is one of the companies that spends a lot of time doing that. I had an opportunity to join them, picked it up, and that's how I'm here today. So I've got sort of two parts to this talk. Atlas is our internal telemetry system over at Netflix, and the thing that really I find very fascinating about it is that because it's such a powerful and reliable platform, it's encouraged an ecosystem of tooling around it in order to allow us to deploy it and operate it in a reliable manner, and also to get the insight that we need out of it in order to help keep the Netflix service stable. So in the first part, I want to spend some time talking about what Atlas is capable of, and what our team does in order to get that thing running in the cloud and keep it running in a smooth fashion. In part two, I'm going to expand on the ecosystem a little bit and talk about some of the additional tooling that comes along with Atlas, or that we've built on top of it, which will allow us to get those additional insights. So Atlas was developed by Netflix to manage dimensional time series data for near real-time operational insight. Atlas features in-memory data storage, allowing it to put together and report on very large numbers of metrics very quickly. The focus is operational intelligence. We disambiguate this from business intelligence because what we have found is, because we've built a platform that's so speedy and so reliable, a lot of people like to take advantage of that for some of their business intelligence needs. A lot of people end up being surprised when they're like, hey, you only store the most recent 14 days worth of data in Atlas. How can I get more data? And the answer for those people is, well, it's persisted out to S3. You can access that through Hive jobs. If you need the real-time week-over-week comparisons, if you need near-minute data, then Atlas is going to be a better use case for your fit. Atlas is open source. I have a link here at the bottom of the page. I will caveat that a little bit by saying the Atlas backend is really the piece that's open sourced. It's got the query layer, it's got the primary backend storage layer. There are some other pieces of the Atlas ecosystem which are not open sourced yet. They may be coming sometime in the future, but we have no promises as to when that will be. So when we say very quickly, what do we mean by very quickly? Very quickly is a bold statement to make from anybody working in technology. So what we're going to do is I'm going to give you a very rude introduction to what we call a stack language. What does the following query do? Name, TCP in segs equals average. We've got some other junk here. Legend, name, TCP out segs. If we break it up and we add a little bit of white space, I think it gets a little bit easier to read. Atlas stack language works in a reverse Polish notation manner. All of the operators are prefixed with a colon. Commas separate all of the different elements of the stack. So really what we're saying is we would like to look at metrics that are tagged that have a name of TCP in segs. I want the average value of that, and I'm going to assign a legend to it. And I would like to take a look at TCP out segs, average of that, and slap a legend on that as well. So this is a graph that I generated. One thing to note is that Atlas runs in each of our AWS regions. So what I did was, by taking that query, Atlas stack language by default has a greedy match mechanism. So if I specify a pretty generic query, you'll notice I didn't add any additional filtering to that on top of just saying, hey, I want to see something about network traffic. It's going to match every single query that has those tags in it. So by running that query in the prod US East 1 region, which is the largest region that we operate in at Netflix, I have produced the following graph with 2 weeks of data. So it's 2 weeks of data. The step size, the amount of data contained within each individual point is 30 minutes. Atlas stores data at per minute resolution, but when you expand time ranges and you limit the number of pixels that are available on the graph, we have to do something known as consolidation. So what we're doing is, in order to be able to draw this graph with this limited number of pixels, we're averaging out all of that per minute data so that 30 minutes of data is represented by each point, right? But it's also an average across a very large number of instances and a pretty large time range. So you still get, this sort of diurnal pattern which represents, when we go into peak and out of peak in that particular region. There are 22.5 million input lines. There are 2 output lines. There are 1.4 billion data points input. There are 1.3 million data points output. This graph was rendered in 1.6 seconds. This graph can render faster than you can think about the query that you want to put in.
Which bit took the time?
What's that?
Which bit took the time?
There's all of it. there's effectively 3 stages in Atlas query processing, right? One is selecting your data points, and then there's an intermediate consolidation layer. After it fetches the data points, it takes those and renders them into an intermediate data set, and then there's the final rendering, which produces the PNG or a JSON payload if you want. I'm going to dig a little bit more into this. I'm going to show you a little bit of the architecture behind Atlas, and we can talk a little bit more about what goes into actually rendering a bunch of this stuff. How do you keep Atlas speedy? Limits are critical. We have an SLA for metrics, which is 5 minutes. If you don't deliver metrics to us in 5 minutes, you've missed your opportunity. We drop you on the floor, and we proceed from that point forward. The output line maximum is 1024. So in the previous graph that I did, you'll notice that I had millions of input lines, but only 2 output lines, right? So I've selected a huge data set to start with, but I've got a very small data set on the output. The reason why that's okay is, in addition to being able to store and select data incredibly quickly, Atlas is very fast at aggregating results. So being able to sum up, different values from, multiple different instances that store the data that we're interested in is a key feature of the system. And because we can do that so quickly, it's okay if you have a large input data set as long as your resulting output data set is limited. If you try and do something fancier and you try and break it out and do a group by and say, oh, okay, it's good enough that you've selected input and output network traffic for everything in this region, but I also want to group it by node. And how many tens of thousands of nodes do we have? That would basically be impossible for Atlas to be able to keep up with and render that as a PNG in any sort of timely fashion. We could do it, but it would take time. There's another strategy that we have that allows us to be able to deal with that. We limit the maximum query time and the maximum concurrency for queries. We have an alerting system that talks to Atlas that allows us to set thresholds, do a little bit of prediction, and then take actions based upon that. So we can send emails, we can terminate, we can talk to PagerDuty. But in order to keep that query load reasonable, we limit alert data to querying the last hour. Atlas stores data for the last 2 weeks, but the last hour is the only one that's valid for alerting. We figured that outside of the last hour, it's not going to bring a whole lot of benefit to you to be able to have an alert that says there's something wrong right now. We have separate stateful and historical clusters, and we also have roll-ups and filters. So if people make mistakes, we have the ability to say, look, these metrics don't make any sense for what we're doing. We would like to drop these on the floor, or we would like to roll these up and remove some of the cardinality from some of the tags. We have the ability to trade latency for data set size. One of the things that was developed with the version 2 of the Atlas API was the ability to say there are some people who want to be able to, for whatever reason, pull data from an extraordinarily large number of instances, but then also group that by node and then perform some additional transforms. The V2 Fetch API is effectively a streaming API that says, all right, fine. If you want more data, you can have more data. You just need to pay for it in terms of latency. People have gotten so used to the Atlas rendering engine being able to return results in sub-second times that they expect that to happen pretty much all the time, regardless of what data set size they've selected as an input and what data set size they've selected as an output. So by providing this feature, we've given them sort of an alternative. And there's several teams that have taken advantage of this, and they've done their own D3 rendering engines to take advantage of some of this stuff. We also do instance and JVM tuning. Garbage collection algorithms and parameters are carefully selected, tested, and tuned. Instance types that we use in AWS are also carefully selected. You might think that just because Atlas is in memory, going immediately to the largest memory size instance you can get in AWS would be a win. That's not necessarily the case because typically, even with the more advanced garbage collection algorithms such as G1 that help you avoid some of the fragmentation that you typically see with concurrent mark sweep, even those start to have some difficulties as you increase the size of your heap space just exponentially, right? Historical clusters also do something rather clever, I think. In the stateful clusters, nearly all the memory is allocated to straight heap. In the historical clusters, we actually split the memory between heap and direct byte buffers. The direct byte buffers allow us to load and store the historical data from Atlas and keep it available, while the heap memory in the historical clusters is used for temporarily loading data out of the direct byte buffer so you can perform manipulations such as consolidation or aggregation. How big is Atlas? The maximum capacity is 2 billion metrics per minute ingested per region. For each of those 2 billion metrics, we store data for up to 2 weeks in memory, and we store years of per minute metrics data in S3, which again are available in Presto and Hive. We have thousands of instances of Atlas per region, and they're relatively evenly distributed between AZs as a disaster recovery strategy. Typically we have multiple mirrors, and what we'll do is we'll say one AZ is one mirror, one AZ is another mirror, and then we'll reserve the third AZ for the historical clusters. Some of these cluster sizes are so large, they put a lot of pressure on Amazon. It makes it a little bit challenging for us to do red-blacks in some cases. But we work pretty closely with the AWS capacity team to make sure that we have what we need in order to be able to pull that off. We are deployed in 3 major regions to support Netflix's regional failover strategy. So 2 billion metrics per minute, that's a lot. How do you get to that? How is that even possible in a world that we're talking about? I think it's helpful to understand what we consider a metric in the context of Atlas. A metric is time series data uniquely identified by a combination of tags. Tags are metadata. A tag is literally a key value pair, strings on both sides. We have a piece of software called Atlas Plugin, which provides 8 useful tags automatically. This provides things like NF app, NF cluster, NF zone, NF region, things that help you uniquely identify your application where you're running in the cloud without you having to provide any data on top of what we're automatically giving you. So you as an application author can be focused pretty closely on the actual application metrics that you want to collect, gather, publish, and we'll give you a little bit of the metadata that helps disambiguate that from the efforts that others are putting in. You can have up to 20 additional user-defined tags. A good tag design allows effective drill down into data with the group by functionality in Atlas. So for this example, what I would like to talk about is we have an engineering tools team at Netflix. And the engineering tools team has recently become responsible for managing Stash, our Git repo. One of the strategies that we have for publishing metrics into Atlas is we've got log parsers, right? So if any of you are familiar with Atlassian products, you'll know that they don't expose tons of extra application performance data through JMX. They give you, whatever the default stuff you get out of JMX. You'll get, GC pause times, GC heap times, a few other things like that. The more interesting data about how you operate your Atlassian products is actually in the logs. So if you want to turn that into metrics that you can then graph and alert and gain some insight into your application, what do? You write a log parser, you have the log parser take that data and spin it back into Atlas. When the engineer who was working on that started doing that, he started off by creating, basically, a name, Stash metrics, and then he created a tag, stash.repo, which was a combination of both the project and repo. Now in Stash, sort of like GitHub has organizations, Stash has projects, right? It's basically just a grouping of Git repositories that you can have inside of the system. So when he ended up coming up with this tag, he smashed project and repo together with an underscore, so it was readable and you could understand it. But the problem was the cardinality on that metric ended up being something like 2,000. And if you want to group, like if you want to be able to determine what the latency on clones is for all of your repos in Git, Stash, and then figure out which one is misbehaving so that you can go figure out what you need to do in order to remediate that, you can no longer group by an Atlas because you've exceeded the 1024 output line limit. So what do? this is a good case where we've got a concept inside of the software project that is a natural pivot point into repos. So he went back and he refactored his tags, and he created a separate project tag and a separate repo tag. And in both cases, the cardinality of neither of those tags was 1,000. We have 50 or 100 repos, or 50 or 100 projects, and then it varies pretty widely among the projects how many repos you've got. So by breaking that metadata out into two separate tags, you can now pivot effectively. You can take a look at the sum aggregation of latency across all of Stash, and then you can break that out by project, and you can see which project is misbehaving. And then once you know which project is misbehaving, you can break that out into repos, and you know exactly what repo is having a problem at this point in time. That helps you figure out who's cloning it, who's possibly taking down your system, who you need to have a conversation with in order to get that situation resolved. So how do you get to 100 million metrics? So we talked a little bit about what metrics are and what metric design looks like. This JSON payload here is an example of how we build out metrics. So the name tag is required in Atlas. So in this case, we'll say, we have an A/B test service. Let's say we're going to call the metric ab.requests. We'll say the NF app tag gets added automatically. It's my awesome app. Let's say we have a request class. It could be success or failed. An endpoint could be any one of those four. And let's say we've got test cell, country, and NF node. And over on the right, I've indicated what the cardinality could possibly be for each of those. One of the things that trips up engineers at Netflix occasionally is they'll spend all this time thinking about their metrics and how they want to design them and what the possible cardinality is, but they'll forget how big of a cluster they're actually going to run this on in production. So you can see in this case, if you run this on a 1,000 node cluster, that's the thing that pushes the volume of these metrics up to the next level, right? So in the Atlas backend, just having a different NF node is the thing that's going to allocate a separate bucket of storage just for that metric. And it's useful from an aggregation perspective, but people tend to forget about that. So in this example that I have here, this takes you up to 2 million metrics, right? Now, let's say, for example, I had 50 other classes of metrics like this that had the same type of cardinality. All of a sudden, I'm up to 100 million metrics. So that's cool. What else does Atlas do for us? So the Atlas backend has the ability to do a bunch of different prediction functions. We support week over week. We support trend, which is effectively a linear regression. We support double exponential smoothing. We have a couple of shortcut functions which provide pre-tuned values for you, or you can provide all three inputs, the number of data points, the alpha, and the beta parameters if you want. We offer an integral function, which will provide sum over time, and we do fun things like rolling count, which is incredibly useful when it comes to figuring out alerting. In the Atlas ecosystem, Servo and Spectator are important. These are both open source projects as well. Servo is the Java library that we use to create and collect metrics. It provides for timers, counters, and gauges. It's been around for quite some time. You can use Servo and have it interface with other metrics backends, such as Graphite if you're interested. That capability does exist. Spectator is a next generation API wrapper on top of Servo. The idea behind Spectator was we wanted to make it easier and more consistent to think about how you create metrics and how you do dependency injection, so that it's a little bit easier to test your metrics generation when you're actually building software. But Servo provides JMX polling out of the box. Servo's got a background thread that'll fire up. It recognizes the fact that you're running inside of a JVM. It knows that you've got a JMX port available if you've configured it, and if that's available, it'll connect. It'll start pulling down all these metrics for you automatically and start pushing them. In context with Atlas plugin, it will automatically send that to the Atlas backend on your behalf. Atlas plugin is a chunk of software that we run internally. This is not open source, but this provides 7 or 8 key features for us that really take the capabilities of Servo and Spectator to the next level. It does that automatic tagging I talked about before. It handles metrics batching, and it uses a binary JSON codec, so it dramatically improves the performance of sending incredibly large volumes of metrics to the Atlas backend. There's some applications at Netflix which send as many as 350,000 metrics per instance per minute to the Atlas backends. When you get to that level, it's entirely possible for Servo and the Atlas plugin to take a dramatic amount of your CPU time, as much as 3 or 4%, if not more. We do have an engineer who's pretty focused on Atlas plugin, Servo, and Spectator. So when issues like that are uncovered, he does spend quite a bit of time doing some performance analysis and trying to figure out how to make that better. Just recently, he was able to put a refactor in for alert processing that increased the performance like 100x. It's pretty interesting. We have support for critical metrics. So critical metrics is a concept where we wanted to have an Atlas stack that was completely independent from the bulk of the Atlas pipeline, so it could operate in the event of major disasters in a particular region. It also handles metrics at a much lower time resolution. So the metrics resolution in critical is 10 seconds as opposed to 1 minute. But it also doesn't store metrics for nearly as long. It only stores them for 2 hours, and we've got an upper cap on the number of metrics that are allowed to go into the critical backends. Again, we have rollups and filters, which can be implemented there. So if somebody checks a change into their code, they pass canary, they push this stuff, and they have it running live. If they suddenly start spamming us, like and doubling their metrics volume, going from 100 million to 200 million, they have an opportunity to implement filters and rollups, which will reduce their metrics volume. We have on-instance alerts and CloudWatch publishing. On-instance alerts are another way to improve the reliability of your alerting. Again, it takes the bulk of the Atlas processing pipeline out of the way, and since the individual instance is responsible for collecting metrics anyway, it can do simple threshold validation against some metric that you're interested in, and when it passes, it will then trigger calls out to our Alert API backend to do emails, terminations, and some other fun things. We also do Atlas polling, so we offer health check polling, Eureka polling. This is internally at Netflix, this is known as Discovery. This is the Netflix sort of am I up, am I healthy system. It's a system that was originally developed because Netflix started running in AWS Classic and ELBs were publicly available. There wasn't really a concept of internal ELBs and VPC at the beginning. So this was our means of being able to locate all the services and effectively do client-side load balancing. So each client would connect to Discovery, say, here I am, register me with this VIP. I would like a list of all these other services I'm interested in, and then it would load balance between them. We also provide SNMP polling. We collect that data and send it into Atlas in the back end on your behalf. Okay, so Atlas. We have an idea of what the features are about. This is what an Atlas global deployment looks like. So what we've got is we've got backends in each of the regions. Now I said we were deployed in 3 major regions. We used the US West 1 region effectively as a test region for ourselves. So we've got the Atlas backend running in each of those locations. In order to have a global view into all the data, we actually have a global service that runs primarily in US East 1, but then we also have an ELB failover in US West 1. And when you want a global view, you connect to this service, and then it knows about each of the regionals. And it will appropriately shard and distribute the query to all of the regional Atlas stacks that know something about the metrics you're interested in, and it will then receive the results, aggregate those, and then produce graphs for you. I wanted to provide this view because taking a look at this, you're like, oh, okay, no big deal. All right, I got an Atlas, I'm gonna put an Atlas in each of these regions, I'm gonna run this stuff, no big deal. Global, sure, that's simple, no big deal. The problem with global today in this architecture is that this was a problem for us earlier in the year before we re-architected a service. We actually have a service called Tunnel, which does SSL tunneling between each of those regions, specifically for the Atlas service, so that the global endpoint can appropriately connect to and distribute queries to each of these regional clusters. Originally we were using an Apache proxy for that. We've since rewritten it in Java. Before, when it was on Apache, we would occasionally just run into connection limits and just blow up the Apache process. And when that happened, we would get incomplete data results, and then that would result in us producing black graphs or black boxes for people because we're like, I don't know what happened to a quarter of your data. I can't give you some kind of reasonable result which represents some aggregation that you wanted to look at from a global perspective. Again, since we rewrote that in Java, it's been more stable. We have plans in 2016 Q1 to re-architect how we're going to handle the approach to global data. But I figured I would talk a little bit more about where we are today. So for each Atlas regional deployment, this is what we've got. So this is the instance and the base AMI, just to give you an idea of all the different software chunks. Here's a log parser that I'm talking about. We use a temporary Redis queue to store that data before Atlas plugin pulls it out and sends it down the pipeline. We've got Spectator as a wrapper on Servo. Servo is where you've got the rest of your metrics. Atlas plugin, working with Servo, will talk to JMX. And then Atlas Client is effectively just a dependency injection wrapper for Atlas plugin to allow bootstrapping it inside of Governator. And then this whole mess is the Atlas backend. So there's a couple of key bits to this. We've got the published cluster. The published cluster is effectively, it's an aggregation cluster. This is the endpoint that all of the instances in every individual region talk to. This is the one service that we have in the Atlas stack that auto-scales using Atlas data, no less. And we actually implemented that auto-scaling algorithm ourselves using our Atlas deploy technology. The published cluster then talks to our stateful tier, Mirror 1 and Mirror 2. This stateful tier is where we store the last 6 hours worth of data. Then we have an hourly tier, which stores the last 3 days of data, and then we have a roll-up tier, which stores the last 16 days of data. And then in order to get a query that traverses 14 days, the regional cluster, which is responsible for implementing and handling the query layer, understands which of these clusters has the data that you need. It will shard the query across each of these clusters, aggregate the results, produce a PNG, and then return that to you. The mirrors, because they're stateful, we have 2 of them. Those are very large clusters. And the reason why we have 2 is because if we lose one node in one of those clusters, we've lost some percentage of all of our metrics data. What we're banking on, though, is that if we lose a node here, we didn't lose the exact same node here. Because each of these clusters, after they've processed an hour's worth of data, they take that data and they send it to the persistency cluster. The persistency cluster is responsible for taking that data and writing it out to S3 as fast as possible. If it gets backed up and S3 is not responsive, it actually persists it out to local ephemeral disk, and it holds it there as long as it can until it can actually get through to S3. In our experience, S3 has been pretty reliable. We haven't had too many issues with failing API calls or backing up data on this disk, and it's been generally okay. So because we're writing 2 copies of this data out to persistency into S3, what are we going to do with 2 copies of data? What happens if we only have 1 copy of data? Well, we actually have an EMR cluster that spins up. We have an EMR cluster that's actually very tiny. It's actually just like a single control node, really. But it's responsible for periodically firing up larger EMR clusters in AWS to take the data that was freshly written into S3, parse it, process it, turn it into a bunch of sequence files, which are then able to be read back into the historical clusters. It's in this EMR processing that we do data deduplication. So if we've got 2 copies, we throw one away. If we've got one that looks like it's the master, then that's the one that's going to take precedence. If there's any data correction that needs to be done, that's what happens in the EMR layer. Once we're in EMR, Hive and Presto now have access to this data, so you can do long-term business trend analysis if you're interested. And then, because that data is now in S3, the hourly and the roll-up clusters can then do their job. Every hour, these clusters evict the most recent hour's worth of data, and they load the next hour's worth of data directly out of S3. The Polar system is a separate cluster that does a couple of things. It uses both discovery and ETA data to figure out what new systems have been spun up in AWS. If you're not familiar with ETA, it is a caching layer that we wrote that caches AWS API data. The problem for Netflix is freedom and responsibility. Lots of engineers get lots of access to the APIs. We don't really restrict who can do what with the AWS APIs. We have ways of delegating keys in a secure fashion, delegating instance profiles, giving people the access they need to get their jobs done. However, if you take that to the extreme, then you've got however many clusters, however many servers, however many developers hitting the AWS APIs. At some point, you're going to get throttled. We've been throttled several times. To help prevent that throttling, we have this ETA service. So the ETA service knows about most of the collections that are available through the AWS APIs. And it scans those every 5 minutes, hits it as hard as it can, gets all the data, stores it in memory, persists the most recent copy out to S3 so that if ETA goes down and comes back up, it can load its most recent state out of S3, and then it's got this in-memory cache. Because it's storing all this memory, it's storing all this data in memory for Netflix, specifically for Netflix, we can very quickly query that to figure out, hey, has a new instance been added? Where does it exist? What ASGs is a part of? How does this whole thing work? So the Polar will notice from ETA that it's got a new instance up, and then it will check to see, is that instance up in Discovery? If the instance is up in Discovery, instances should register a health check with Discovery. The Discovery service needs to know how it can determine if an instance is up or not. There's a lot of debate about what a good health check is. In the Netflix view, a good health check is short and sweet, 200 OK, right? The reason why that's a good and valid health check, particularly in the cloud, is the fact that you can get a 200 OK off of an instance means a whole lot of stuff works right. Your networking is working, your routing is working, your DNS is working, your port is up, your Apache's running, your Tomcat is running. You have enough CPU and RAM available in the system to be able to process that single request whenever you ask for it and return it in a tiny amount of time. There's some people who have the opinion that you should do a deeper health check, maybe validate persistence, either a database layer, or can you write to disk, or something else like that. The problem with those style of health checks is as soon as things start to go wrong, those start becoming incredibly latent. You start putting additional pressure on your persistency systems. It can cascade into a whole series of challenges that maybe you don't want to deal with when you're trying to keep your service up and healthy. Once the Polar has that information, it talks to a pre-configured SNMP-D on each system. So we yank a whole bunch of low-level Linux system stats out, and it starts checking the health checks. The health checks are actually handled by a separate cluster. It hits those, and then it publishes that stuff back into Atlas. In terms of this cluster over here, this is a representation of some of the additional tooling that we have. I talked a little bit about the global cluster, which is capable of providing global views for Atlas. There's the Atlas UI, which we have developed to make it easy to browse tag space and put together graphs. There's the Alert UI, which serves as a user-friendly front end for creating alerts. We have the Alert on Queuer, which is actually the alert service responsible for doing that last hour of data checking and threshold validation. And then we have dashboards. So as you find metrics that you're interested in, you are capable of saving that and accessing that in quick fashion.
So Matthew, if you're a product manager at Netflix, how do they take advantage of all this capability? So certainly you've shown a very scalable way of collecting a bunch of metrics.
So that's an interesting.
Product, what do I do with
So
this?
that's an interesting question. So product managers at Netflix.
Or I guess I'm making an assumption. Who are your primary customers, and what's the business benefit, or what do they do with it?
So okay, so let me answer your question in two ways. So product managers at Netflix have a slightly different job because the product at Netflix is streaming movies. Our goal is to win moments of truth. When you go home at the end of the day and you sit down with your family and you say, what do I want to do to relax this evening? If you choose Netflix, we win that moment of truth, right?
Netflix and chill.
Somebody that's another way to go.
Somebody had to say it.
That's another way to go. So if you choose to spend your time with Netflix, then we've done our job right? We've made it easy for you to find something that you're interested in watching. So product managers are really focused on content selection, the Netflix application user interface across all of the different devices that we've got, right? That's where those guys tend to spend a lot of their time. They spend time with algorithms, right? We actually have teams that work on algorithms, but they'll try and figure out what's the right question that we should ask, that we should attempt to answer with our algorithms. So product managers in and of themselves don't spend a lot of time with this system. This system is mostly used by our cloud control plane, right? So there's really effectively two parts of Netflix, right? There's the content delivery network that we've built, the Netflix Open Connect service, right? And then there's the Netflix cloud control plane, which sits in AWS, which is what we're talking about here. So we're talking about the Netflix API, the user data, the signups, the billing, right? All of that stuff. So, when you sit down at home and you flip on your Apple TV and you're like, yes, let's play some Netflix, what has to happen? Username, password, authentication. We have to allocate you a license so that you're allowed to stream whatever content is you've just selected to play that particular evening. All that stuff is happening in the Netflix Cloud Control Plane. That happens through the API service, which is effectively the front door to the Netflix Cloud Control Plane, and then that's where the microservice architecture takes over. There's just hundreds of services that sit behind that, which answer the calls of the API service in order to put together this experience so that you can watch the content that you want. So Atlas is primarily for the microservice application owners that operate the Netflix Cloud Control Plane.
Okay, thanks.
Sure.
I'm curious on the publish mechanism. Is that ever a bottleneck?
Fun question. Before we figured out how to implement our own version of auto scaling for that, it was. We actually had a couple of incidents in the past year and a half that I've been at Netflix where we've dropped metrics on the floor for a couple hours because we were having some issues with that capacity. When I first arrived, what we were doing is we were statically sizing that publish cluster, and we were effectively running it twice as large as it needed, because if something goes bad, we're the first system anybody in Netflix takes a look at to figure out what's wrong with their system. So when you're having a problem, whether it's something going funky with AWS, like DynamoDB, or maybe there's something going on with Ultra DNS, you never know. Our system is the first thing people are looking at to figure out how it's going. So we effectively just basically double size the thing. So we said, you know what? If something bad happens, an API needs to double size all their clusters, we can absorb the capacity. We attempted to refactor the publish code and put it on larger instances, and then we got really excited about being super efficient with our instances, so we really crushed it down, so it was sort of like a 1.2x multiplier. That's when we started to have problems dealing with some of the auto scaling and failover activities that were going on. However, noting that was a problem, our team spent a bunch of time figuring out how to do auto scaling, and this is actually kind of clever. So this actually fits in really well with the next two slides. So let me talk about this, I'll talk about that, and I'll explain how we solved that issue. So when you have a large collection of clusters, like I just showed, that's necessary in order to present the Atlas data platform, the Atlas experience, what do you have to do in order to keep that thing running so you're not experiencing downtime? Red-black deployment is the answer. So remember I talked about the publish cluster effectively tease data. So when we want to do a deployment of one of our stateful clusters, or any cluster for that matter, but the stateful ones are a little bit more interesting to talk about in this case, because that's where we pay a bigger price if we end up losing a lot of stuff. So we're teeing data here. Effectively what we do is we add a third mirror and we triple publish the data for some period of time. And then what happens after this stage is we sit and we wait. We sit and we wait because we allow these mirrors to become completely full of the data they're supposed to be processing. So we wait for 6 hours for that. And at the end of 6 hours, we make this mirror active, we test out the data, we validate that everything looks good, and then we harvest the previous one, and then we repeat the process again. Let's contrast that with a rolling red-black deployment. This is the technique that we're using for the Atlas Publish clusters to help solve that problem. One of the issues that you can run into with a full-on red-black deployment is, in order to do that successfully, you need to be able to get all of your capacity right now from AWS. And depending upon what's going on in AWS, both within the Netflix ecosystem and the wider AWS ecosystem, there may be a crunch for capacity that you need. So if you're like, I need thousands and thousands of instances, and I need them right now, and I need that alongside all the other thousands of instances I've got, AWS might be like, not yet. You're just gonna have to wait a little while, right? A rolling red-black deals with that in a slightly different fashion. So here we have our current cluster up and healthy, doing what we want. And then what we do is we say, hey, for some small percentage of this cluster, spin up a new ASG with a new version, and let's wait for those to become healthy. As soon as those instances become healthy, mark the same number of instances out of service and harvest them from the previous ASG, and then repeat that process until the previous ASG is completely drained and decommissioned and the new ASG is up and running. So with the Atlas Deploy service that we've got, we leverage the Atlas Critical Metrics cluster. So that's what's storing metrics data at a 10-second interval. And when we wrote the Atlas Publish service, because we wrote it, we knew what the key metrics were. And in this case, for the Atlas Publish service, the key metrics is both inbound data volume and outbound data volume. By taking a look at both of those two metrics, we could basically see if there were any dramatic increases or dramatic decreases in that. We could apply a linear regression to that, and we could predict for the next 5 minutes, our cluster size needs to look like this. And because we're using Atlas Critical Metrics, it can react every 10 seconds. We can effectively go up 1, down 1, up 1, down 1, up 5, down 5. We can adjust incredibly quickly to the demands that are being placed upon the cluster. Since we developed that functionality, we haven't had any dramatic issues with dropping metrics on the floor as a result of capacity.
Is there any buffering in any device, like I don't know, load balancing functionality before it even gets to the publish? So like, let's say it's like 1 second delayed, like you didn't spin it up just fast enough.
Oh,
and
so
you need 1
it's
second more. Is there some sort of
yeah. So 1 second delays are not really a big deal for Atlas. So if we flip back and we take a look at this, so the Atlas plugin scans your servo metrics registry once per minute, and it's like, hey, all right, these are all the metrics. These are the things I'm supposed to send. So pulls all the latest timer, counter, and gauge data, grabs it all up, sends it in that batched binary codec fashion straight to the Atlas Publish cluster. Now, if there's like, let's say there's a network hiccup. Let's say, a packet gets dropped along the way. If it has to retransmit, it'll simply retransmit. And as long as it's within that 5-minute window, I mean, it's got a timestamp associated with it. It knows what it's supposed to send. It's got a timestamp for that. And then the Atlas Publish cluster is just doing that 5-minute window validation.
The plugins aren't necessarily like blindly spewing metrics. It's a synchronous write rather than asynchronous. It essentially makes sure that it's successfully published.
It's synchronous. It's synchronous in the way that TCP is synchronous, right? Like there's no additional validation in the Atlas software that's keeping track of, I expected you to send 100 metrics, because it's opportunistic publishing, right? Think about the difference between Cacti and Graphite, right? One of the revolutionary ideas behind Graphite was, I don't need to predefine what it is that I'm gonna send. I can just spin up a new instance, create a bunch of new metrics, I can push a bunch of data to you, and if I don't care about it, I can then go delete it. Cacti and RRD, on the other hand, you have to predefine. These are the things that I care about. These are the graphs that I want to look at. You have to spend a bunch of time pre-configuring the system. Atlas and Servo, on the other hand, take that Graphite style approach. You can publish what you want, when you want. You can spin up instances, tear them down. We'll happily accept the data as long as you're presenting it to us in the correct format.
Right. Okay. Very cool.
Okay. So red-black deployment. If anybody has spent any time doing red-black deployments in AWS, this is approximately the 12 steps that you need to follow. It's a lot of work. If you are going to do that by hand for clusters with thousands of instances in 4 regions, you're going to get pretty bored pretty fast, and you're going to want to find a way to automate that. So our team, when we were trying to figure out how to keep this stuff up and running, and get these deployments done in some sort of reasonable manner, we took a look at a bunch of automation options. At the time that the Insight engineering team started building and deploying Atlas, Asgard was still primarily the internal deployment automation tool at Netflix. Spinnaker was just a brand new project at that point in time. They were still figuring out, how they wanted to, break things out into microservices, and how they were going to be thinking about the entire continuous deployment problem. Spinnaker was released open source just yesterday, so I encourage you to take a look at it. It's a pretty piece of software. It does some interesting things in terms of CD pipelines, but at the time my team needed to solve this problem, Spinnaker wasn't fully there for us. And there's a couple of features that we still want out of Spinnaker that aren't there yet, but we're on the list. We just got pushed down a little bit so that they could focus on getting their open source release out. CloudFormation, kind of, you can do that. CloudFormation's pretty powerful today. I don't recall what the limitations were when we first started needing this level of automation, but I think one of the things that's a little bit tricky about CloudFormation is you're writing a lot of stuff in JSON, which is a complex format that has a lot of internal intro references, and then it organizes things in the manner of stacks. So you have to be kind of careful about how you define your stacks and how you organize those in the cloud, and what do you do if you want to just like completely delete them. And then CloudFormation can just be tricky. There are some people who are leveraging it quite well today. One of the teams over in IT Ops is actually using CloudFormation for all their deployments, and they're reasonably happy with it. But we wanted to have more individual resource level control over all of the different AWS resources that we were going to use. Elastic Beanstalk didn't feel like a very good fit for us. It's a little bit more like sort of the Heroku style Git push and whatnot. Part of the reason this doesn't work for us is because we're using a Scala stack and a little bit of JavaScript in there. OpsWorks, again, it's an interesting piece of technology, but it didn't feel like a particularly good fit. Chef Puppet, Ansible, and SaltStack. For anybody that's spent any amount of time doing AMI red-black deployments, you'll know that these tools are good during the provisioning of your AMI and getting your initial software set up. But then once you've got that set up, you're creating launch configs and creating ASGs. Like, you shouldn't be touching the bits after you've already baked your AMI. So because of the bakery technology that we have in place, we actually leverage Chef just a little bit. But my team doesn't really need to know about that because that's all wrapped up inside of a tool known as Aminator. So my team created a tool known as Atlas Deploy to help manage all of this. So what we do is we have a configuration input pipeline. Actually, I guess I should probably back up. Atlas Deploy is a stateless, multi-threaded deployment automation service that enforces immutable infrastructure with declarative desired end state configuration. That's about as many 10-cent words as I could throw into one sentence. But in practice, what does that mean? We have a configuration input pipeline. So what we do is we have deploy configuration scripts, which are written in Groovy. And this is where the declarative state comes from. In Groovy, we are able to specify, this is what I want my deployed Atlas stack to look at. These are all the clusters that comprise it. These are how these need to be deployed. These are what the security groups need to look like. This is what the ELB needs to look like. This is what Route 53 needs to look like. This is the AMI I want to use. This is the build I want to use. I need you to take this AMI, take this resulting package, bake this, and then create a launch config, spin up some ASGs, and make things happen. So how we operate is we have a copy of this deploy config locally. We'll make some changes to this. We'll push it to Stash. Stash will then notify Jenkins that it's got to change. Jenkins will build the job. So part of the reason we're using Groovy, right, is also because we can get validation of our configs, right? It's very easy to bend Groovy to your will. We've got a nice default set of models which understand the valid strings for AWS. So like instance types and ASG configurations, a few other things like that. And it'll do that validation. If we fail validation, obviously the developer that failed the build will get notified and we can fix it. But when we're successful, the output of that job is a giant JSON payload, and it's organized by region and organized by application. And we push that into S3. And when we push that into S3, Atlas Deploy constantly scans that bucket looking for updates. And when it sees an update, it pulls it down, it processes it, and it now loads a new desired end state configuration into place. Once it's got that configuration into place, it's like, okay, what changes do I need to make in order to make this happen? So if we talk about any piece of software that's comprising Atlas today, it's useful to think about the application build pipeline. So we'll have application Git repos. So let's say, for example, we're making a change to the Atlas backend. So we check something in, we push it to Stash. Stash notifies Jenkins that something is different. Jenkins does a build. It'll do our application build. It'll do our application tests. And then as a result of that Jenkins build, we publish a Debian artifact. So we'll create that. It'll get stored on the Jenkins server, but then it'll get published to Artifactory. Once we've published it to Artifactory, given the desired state configuration that we have in Atlas Deploy, Atlas constantly monitors Jenkins. So one of the things that we can do with Atlas Deploy is we can say, I would like Atlas backend to have XYZ version of software. Or we can say, I want desired latest version. So if I say desired latest version, then it's always going to take a look at the most recent successful Jenkins build and use that artifact version to determine what it needs to do next. So let's say, for example, I've got an Atlas historical cluster up and running. I've pushed a new build. I've got a new version. It's set to desired latest. Atlas Deploy says, oh, well, new artifact in Jenkins. Hey, bakery, I need you to make me a new AMI. So one of the things that's nice about working at Netflix is we have an engineering tools team that produces base AMIs for us. So that's an Ubuntu trusty or precise base operating system configured to a minimal standard, which has a bunch of additional tools and packages installed that makes it easy for us to run inside the Netflix ecosystem. So we get, the current approved version of Java, the current approved version of Tomcat. We'll get a little bit of environment variable set for us. We'll get some log rotation. We'll get a few other things set up for us. We'll have the Apache proxies already configured and in place and ready to run. So we take that base AMI. The bakery is then responsible. So Atlas Deploy, when it talks to all these services, obviously is just using an API. But we talk to bakery and we say, hey, look, there's this new package. I need a new AMI. It uses the base AMI as a starting point. So it mounts that up. It installs the Debian package that we've just produced locally, any dependencies that that thing has, produces an AMI, returns that value to Atlas Deploy, and then Atlas Deploy talks to the ASG service. It creates the launch configuration. It creates the ASGs. It double checks the ELB security groups and fast properties that need to be configured for the system. So one of the things that I think is kind of interesting about working at Netflix is, so once you've adopted this idea of immutable infrastructure, right? Like you've produced a build, you've locked your bits in a Debian package, you've locked your bits in a base AMI, and you've locked your bits in the final deployment AMI that you're going to use. How do you change that software? How do you change the configuration? So Netflix's answer to this is, the open source version is known as Archaeus. Internally, we call it the fast properties of the platform service. What that is it's effectively a key value store that allows for scoping. So the scoping that it allows for is you can say, hey, look, in this region, in this zone, for this application, I would like to introduce these configuration properties. So if you build a Netflix application using our platform libraries, it comes with support for this service. So as your application bootstraps or as you define dynamic properties inside of your application, it will periodically scan that service and say, should I apply some value that you have defined for me, yes or no? So because we have that service, like one of the challenges that other teams at Netflix faced was, like, the service is incredibly powerful, right? But the service didn't have a lot of automation for creating multiple explicitly scoped properties for individual regions and individual clusters. You can do it yourself, but it's a lot of clicking, right? But you might have to do that for 4 regions in test and 4 regions in prod, so you're doing it like at least 8 times. And maybe your configuration is a string that's like, a K long or something like that. So a lot of teams cheat, and what they'll do is they'll create what's known as a global property. So they'll basically say, look, for all regions, for this application, I just want this to take effect, right? So when you remove that explicit scoping, it opens up the opportunity to start having configuration problems if your configuration drifts, or you've got different versions of your software running in different locations. So I think one of the inherent advantages that Atlas Deploy brings for us is we basically say, look, these are the properties that we want, and this is where we want them. Because we define that in that declarative state configuration, it just enforces it. And because Netflix is freedom and responsibility, anybody can go in and change people's properties. But the responsibility is you have to know what you're doing. Are you attempting to help that team? Are you doing this correctly? How are you validating your change? But in the event that mistakes are made, this system watches those fast properties and constantly resets them to the values that we expect them to be. So here's the instance view of Atlas Deploy UI. So Atlas Deploy is, like I said, primarily this multi-threaded Scala server. We typically run 2 per region. That way we've got some backup. And they are not coordinated in any way, shape, or form. Like, they just sit there and they load up the current desired state configuration. And as soon as they've got it, they just start hammering APIs, trying to make things happen. And they keep trying until the configuration actually succeeds. So in order to help us understand what state we're currently in with all of the systems we have deployed, we have the Deploy UI. So what we've got is we've got a list of regions and environments, and each of these dots represents an individual instance. So here we're looking at the test region, or the test environment, and we're looking at status not up. So you can see we've got some red dots. Here's an instance that is currently failing a health check. We've got blue dots, which are instances that are probably out of discovery. They're probably in the process of coming up. Some sort of auto-scaling activity might be going on there. You can see here that we have, so this block right here, this represents the cluster, and then these represent the individual ASGs. So here you can have up to 5 ASGs for any particular cluster. Now, the fun thing about, and I don't know how many people actually realize this, but the fun thing about how Netflix has applications, clusters, and ASGs defined is these are not concepts in AWS. Like AWS doesn't have a cluster concept. AWS doesn't have an application concept. We have them because we have consistent string matching applied across all of these constructs, right? So the way that we have the string matching implemented, there's actually an open source library called Frigga, which is a Java library which will enforce this parsing. But basically, the application name comes first, and then it's a dash, and then it's a stack, and then it's a dash, and then it's the ASG name. So the fact that we've got this amount of string data, on the left of some dash somewhere is what actually makes it a cluster. And then the fact that this has some additional identifying details, the thing that makes it an ASG. Like we've implemented versioning inside of ASGs. We use 3-digit versioning, so it'll be V000, V001. So that way we can keep track of what version ASG we've got possibly associated with some particular version of software. So here you can see that we're doing some testing. We're trying to bring up Atlas Published Main. We've got 5 clusters. We started out with 179, 180, 181, 182, 183. And then if you click any one of these boxes, you get this instance view. And this instance view, like this Atlas Deploy UI, like whenever we're doing deployments, like this is our go-to tool. This is how we pull this stuff off. Because it takes all the information you need about instances, about ASG health, and it puts it in one place where it's easy to get access to the rest of the information that you need. So it tells you the instance ID, it tells you when it was created, it tells you your discovery status, your health check status. We've got convenience links for builds. We've got convenience links for Spinnaker. We've got convenience links for Atlas Deploy data, for dashboard data, for Apache logs, for Tomcat logs, and we can even terminate instances directly from this view. So it's not an uncommon thing for us to go in here, hit not up, take a look at something, and if it's like a stateless cluster, okay, that's dead. Okay, AWS is acting up today. Let's just terminate that instance and bring up the next one. This is the desired state view. Here in this case, we're looking at the tier 2 hourly main cluster, and you can see that the current state, the minimum capacity is 12, the maximum capacity is 12, but our desired state is 20. This is just how we expose critical data about what's changing with our desired state so we can understand why a new ASG is coming up. And then this is the events view. I pointed out this Atlas Published Main cluster here. You'll see we've got a red event. This is basically Atlas Deploy flagging us and saying, you're trying to bring up 6 ASGs, 5 is the most you're allowed to have. The reason we put that limit there is so that we don't break ourselves and we don't go nuts creating ASGs infinitely. So with these convenience links, particularly these dashboards, we have this admin view. I think this is actually pretty slick. I don't know how many people think about this, but when you're running in the cloud, it's kind of useful to give yourself hooks to be able to gather data about your running instances. So the Netflix platform libraries give you this capability. Between how we have our base AMI structured with the additional packages that we add, plus the base server capabilities, you can get a lot of information about instances. And this is all locked down, so you can only get access to it from Netflix IP addresses, which is pretty nice. But this is the base server alerts tab. So our team in particular is responsible for providing 2 of these tabs. So we've got the alerts tab and the metrics tab. The alerts tab, this shows you on-instance alert processing. So when people have loaded up a whole bunch of on-instance alerts, sometimes they'll be like, hey, Insight team, I can't figure out why my alert didn't fire. I have this defined. It's an on-instance alert. What's going on? So if they can tell us the instance or the cluster, we can start taking a look and seeing what data was gathered, what alert was defined, has it gathered the alerts configuration correctly, what do we need to do to figure out what's going on with that instance. Here's an example of the Archaeus data. So remember I talked about fast properties, that's what this is. This view is incredibly useful because, again, if somebody's like, hey, we're not able to publish metrics, we can take a look at what properties they have loaded, both defined in their application at build time and also defined in the fast property system. This shows us how they're resolved on the individual instance so we can know for sure what a property value has so that we can validate that it's correct. The base server jars is a listing, literally, of every single jar that's loaded into the particular application that's running. This is useful for us because we publish Atlas Plugin, Atlas Client, we have Servo, and we have Spectator. We have 4 client libraries that we're interested in. These were installed on every application, right? How do we know that they're running the latest, greatest version? This is the thing that gives us that answer. We're able to use this data and turn it into something a little bit fancier that we call the quarterly client deprecation cycle. We actually have a separate service that goes out and scans this data for every single, for one representative instance of every single ASG in all of the regions, and then reports that back so that we can then set some targets and then figure out who's compliant, who needs to rebuild their application and redeploy. Base server metrics. This is the metrics tab. One thing I would point out, I'm super pleased at how this is actually implemented. It's really very clever. So it turns out the platform base server in this particular case has like just enough HTML and JavaScript to bootstrap an off server service. So this is like there's just a tiny little chunk of HTML that pulls down a script from an external HTML or from an external web server that loads this sortable, this highly performant web worker enabled metrics view. So it's like base server itself has these API endpoints that just give you these like JSON payloads, and some of these tabs are actually baked into the service, but this one is actually separate. And the fact that this is separate is kind of nice for us. This actually lives on the Atlas static service. The reason why that's nice for us is because it's incredibly quick for us to rev the Atlas static service. We can basically update this page inside of 5 minutes, and as soon as we update it in that one place, anybody who looks at this tab 5 minutes later is going to get the updated view. It makes it awesome for troubleshooting, it makes it awesome for fixing bugs, it makes it awesome for rolling out new features. Okay, so we've talked about how big the deployment is, we've talked about what we do to automate those deployments. So when we're in the middle of rolling deployments, how do we determine where we're at? So this is a case of Atlas monitoring Atlas deployments. This is the primary dashboard that we use when we're doing back-end stateful deployments. This is a graph showing the number of metrics received for the past 3 days in US East and US West. And then this is the index size. That's the total number of metrics that exist. You can see again this diagonal pattern as we go through peak and then through trough. So what will happen is, like, if I start up that third mirror, just like I described, you'll see like a tiny little line start out here, and it'll slowly start creeping up until it meets up with all the rest of the lines in about 6 hours time. So as soon as I see those lines match up, we know that we're good to go, we're ready to do our testing, and we can proceed with our deployments. I've spent a bunch of time talking about the Atlas deployed declarative configuration. So I thought I would show an example of this. This is for an application that we call Netflix and Grill. That was a Hack Day project. I've got some pictures of that at the end of the presentation. If I end up running short on time, I'll show you that stuff real quick. Fair enough. Fair enough. I have tons of slides. I will not be crushed if I don't get through them all. But what we do is, this is an example of the Groovy, right? So what we do is we define a class, we set up some loggers. This is a case where we're saying, hey, I want the build number to be desired cluster state latest. This block here defines an ELB. So we have an ELB with a name, with a global DNS name, and we define listeners, load balancer ports, instance ports. We define an application. This is where we start doing that string matching that I talked about earlier. So we have an application name here, we've got a description, we set up owners, and we set up security group ingress, and then we set up what our desired cluster state is. We say our desired cluster state should be that application, it's going to be in VPC, I would like to have an ELB, the build name from Jenkins is going to be this, the build package prefix is going to be this, and the build number should be that. We then clone all that out and say, all right, that's my final desired state right there. I would like to have, one of these nodes. I would like it to be in test US West 1. I don't need any fast properties, and I want it to be running on an M3 large.
So Matthew, as you wrap up, maybe one request. So obviously this is black belt level telemetry. For the folks that are more in the white belt kind of just starting to look at this stuff, your ideas like wisdom passed down, if I'd known this when I started, kind of thing, places to look, places to start.
Dude, it's tough, right? I'll be honest with you. When I was working at Blackboard and I was the guy trying to figure out how to take our applications into the cloud, like our first footprint, I was like, what am I going to do? How am I going to possibly monitor this stuff? CloudWatch is an option, Zabbix is an option, Graphite's an option, right? But the problem is, like each of those things, you have to spend enough time with each of them in order to get it tailored for your environment so you can have that, instance comes up, instance goes down, you're still reporting metrics and you're aggregating it at a useful application level so you can make decisions about how to run your service. When I did it, I opted for Zabbix. Zabbix out of the box, at the time that we were doing it, didn't have awesome support for ephemeral instances in the cloud. Their support for that is a lot better now. I think Graphite out of the box supports ephemeral a little bit better, but the challenge with Graphite is scaling, and scaling in the cloud, because people have heard about those Graphite deployments where it's like you need to slap a lot of RAID disk behind it, a lot of fast disk, a lot of SSD in order to keep it happy. I was looking for something like Atlas. I wanted Atlas so bad. I went to reInvent and I saw the Atlas presentation. I was like, yes, I want that. And they were like, open source soon. I was like, all right, fine. It is open source now, but it's not quite in a state where it's easy for you to deploy at the scale that we do, or even a scale where it's going to be particularly useful for tens of servers. We hope to improve that story. I'm one of the guys working on that, trying to explain the deployment of that and the use of that in a slightly more user-friendly manner. Again, we don't have any timelines on it. We'd like to do it. I guess my advice to people is take a good hard look at what's available out there today. I would probably say start with Zabbix, start with InfluxDB, start with Graphite. Those seem like the three leading contenders right now. When we get a little bit further along with having a better deployment story for the general use case, take a look at Atlas. And then figure out how to deliver your application metrics into that, right? In the Graphite world, StatsD is kind of how you do that. They provide client libraries for all sorts of different languages, which makes it easy to plug in. It does UDP aggregation and sends it to the back end. This is what we're doing with Servo and Spectator. If you're comfortable using Java, Servo could be a good solution for that as well.
How long do you spend in meetings talking about how to name your services?
So if you're the Spinnaker team, quite a few. If you're the Atlas team,
It's the hardest problem in computer science,
it absolutely is. It absolutely is. And Netflix, I don't know if you caught Dave Hahn's talk from reInvent where he talked about day in the life of a Netflix engineer. Instances are not pets, they're cattle. You don't get to name them.
How big is the engineering organization that maintains all of Atlas?
It maintains Atlas.
Yeah. Let me ask it again for the. How big is the engineering organization that maintains all of Atlas?
So the Inside Engineering team has grown recently. We've added a couple of other functions. That team has grown to encompass production network engineering, real-time analytics. The core team that supports and builds all of the software that Atlas does is 5 people. So 1 DevOps engineer and 4 platform engineers. Yeah, that would be the other takeaway, I guess. If you have the opportunity as an organization to actually invest serious engineering effort into a metric system, it can pay off.
I have one other question. Earlier when you were talking about what constitutes a metric for Atlas, you briefly mentioned tags and dimensionality and the cardinality of the metrics. So do you create a unique time series for each set or each possible combination of dimensions or tags? I mean, in our world we call them dimensions, but it's basically the same thing.
That's right.
Yeah.
Every time the Atlas published layer sees a new set of tags come in, when it sends that to the back end, it's like, hey, new set of tags. The back end slots it appropriately in a consistently hashed ring across all the instances.
So do you have to have an ongoing conversation with developers about dimensionality and tagging to make sure that they don't explode cardinality?
That's a good question, and we do have an answer for that. So
automated way of shutting them off when they do.
Well, so that's the thing. So because of the Netflix culture of freedom and responsibility, having quotas feels wrong. Right. We trust that you're going to operate with enough context to understand the impact that you're having on the systems that you're going to use. And if you don't, we're available to have those conversations with you. So one of the ways that we have those conversations is we have a self-service tool called Metrics Report. You are looking at the metrics volume from US East and US West for the past 6 months. That's the 2 billion line, right? So with this tool, we've made it easy for teams to look at the total volume, but what I didn't show here is there's a table down here that's sorted by application. So you can click on your application and be like, wow, I'm doing 250 million metrics. Why is that? And then this tool has actually helped expose a number of different tag cardinality explosions that have happened, some on purpose because people were experimenting, some that were, mistakes that were made, right? When we identify those, we let people know, and we sort of deal with that as best we can. The other thing we've got too is we've also introduced an unused metrics report. This one I think is kind of fun because people were looking at the metrics report and they were like, okay, it's all well and good that I'm producing 250 million metrics. Which ones can I get rid of? Who's not using these? This report, this is the result of a daily Hive job that takes a look at all of the Apache request logs on every single regional cluster to figure out what metrics people actually asked for graphs for, whether it's for a dashboard, whether it's for an alert, whether it's for interactive Atlas UI exploration. And we figure out there's some whole set of tags that are never even queried, and it's not an inconsequential amount. Using this data, we're able to go back to teams and say, look, you're not using this. Would you please roll this up? Try it out. Let us know how it works. And because I promised, this was effectively our IoT play on Atlas. We ended up hooking up 18 thermocouples to a grill, some pork butts and spare ribs, and we smoked meat overnight, and we had Atlas alert us when it was time to stoke the fire. I got woken up 6 times that night.